All right, good morning, everybody. I would like to welcome you for 3 media conferences, now at 10, at 11, and 12, concerning the achievements that have been made within the IODP program. IODP stands for Integrated Ocean Drilling Program, and IODP means 3 partners, that is the US, Japan, and a consortium of 17 countries called ECORD, European Consortium for Ocean Research Drilling. But whereas the US and Japan have research vessels of their own, drilling vessels of their own, the JOIDES Resolution and the EGU, Europe does not have such an instrument, but Europe, the ECORD consortium, is organizing very special expeditions, going to waters where EGU and JOIDES Resolution cannot navigate. That means icy waters, like 2004 to the Arctic, close to the North Pole, we were drilling there, or shallow waters, like 2006 in Tahiti, and like in 2009 in offshore New Jersey. And I would like to introduce the 2 speakers. That is Dave McInroy. He was staff scientist on the New Jersey Shallow Shelf Expedition, which we are concentrating on now. Dave is with the BGS, British Geological Survey, based in Edinburgh. He's a geoscientist. And then I also would like to introduce to you Jean-Noël Proust. He's in the Department of Geosciences at the University of Rennes in France, and he was one of the co-chiefs of, so to say, the expedition leaders of this expedition. You should know that each of these IODP expeditions have 2 co-chiefs. The other was Greg Mountain from the US, from Rutgers University in New Jersey. He cannot be with us, but I think Jean-Noël has to tell you quite a bit. But I would like to start with Dave. Dave, you are staff scientist, or you were staff scientist on that expedition. What does a staff scientist do, and how complicated was it to get this project running?
Okay. Yeah, so my job as staff scientist on the New Jersey Expedition was to coordinate the scientists and the science that was done both on board the ship at the time last year and also at the subsequent onshore science party, which took place in November last year. I work for the ECORD science operators, so it's our job to put together what's known as mission-specific platform expeditions. The Americans have a dedicated ship, the JOIDES Resolution. The Japanese have the EGU. We don't have a dedicated ship. We have to contract ships in on a case-by-case basis. And it's quite a complex task to contract these ships, which often don't have drill rigs already installed on them. So we have to find a drilling contractor and actually build a rig onto these survey vessels, or in the case of New Jersey, it was a lift boat, a 3-legged lift boat, and we had to build a rig onto the side of the boat to drop off the side down to the seabed, and Jean-Noël will show some pictures of that. So it's quite a complex job for ESO when putting these expeditions together. And I think, Jean-Noël, you want to now show us some results from the expedition? Yeah. Okay.
So welcome to the Expedition 313 in the New Jersey Shallow Shelf. The main goal of the New Jersey IODP Expedition 313 was to quantify the magnitude and rate of past sea level change. And the expedition was run in May, June, July last year in the offshore, and we opened the core in November and December last year too. So what I'm going to talk about today are just preliminary results. Retracing the history of global sea level change is a challenge for the future of our planet, because sea level is rising. Sea level is rising at 3.25 millimeter per year today, but we estimate a 1.8 millimeter per year for the last century. This is compelling, this is urgent, but the centennial scale is not the whole story. Because sea level rose before, as attested by those marine strata lying right in the middle of a continent today. And sea level rose before more than 100 meters, and at a rate that encompassed 20 to 40 millimeters per year. But causes and effects of sea level change are multiple, and they act at different scales. And what we have to do, the challenge, is to untangle all these causes and effects by drilling in shallow water platforms. Shallow water platforms are really a good place to untangle the multiple parameters. But our knowledge is still very limited today because of the unpublished industrial data on the synchronicity of unconformities on different margins worldwide, because of presupposed ideas on the sediment response to sea level change, and the low precision of the calculation of amplitude of sea level change with delta O18 by 20 to 50% probably. So to do that, we drill 3 holes in the middle of a shelf in the New Jersey, for 45 to 65 kilometers offshore from New York. And these 3 holes are right in the middle of a previous dataset acquired largely by IODP in the offshore and onshore. So these all complement a dataset which was already quite large. This data will help us to measure the magnitude, the time and rate of sea level change, to determine what controls sea level change, glacier, climate, sediment input, more, and to learn how sea level relates to change of shoreline position, crucial today, nearshore ecosystem, nutrient and sediment transport from land to sea, chemistry of pore water below the seafloor, very important too, and the extent of biosphere buried under the seafloor. This was our platform. It was 80 meters high and 45 meters large. This platform was owned by Monco, and the drilling was run by DOSEC. To board the platform, it's very easy, and you just follow the food in the big container MO there. And you met there a good bunch of people made up of 5 scientists, 13 technical support staff from ESO, 9 drillers, and 8 ship's crew. We drill 750 meters below the seafloor by using a set of pipe which are just downsizing. You see the 3 set of pipe that are just undersized from one to the other. And we drop down and pull off the core barrel, which contain the sediment, the 3 meters long sediment core in a plastic liner. This is a sediment core in a plastic liner on the left-hand side. So we have now 3 very nice data sets through the cliniform below the shelf of the New Jersey. We have an excellent core recovery, which helps us to define lithologies and, more important, the depositional environments. Color box are cores where we are defining lithologies, and blank area are places where we have no core. So recovery in those large cliniform is quite good. And it's especially good because it's a lot of sandy sediment, and it's difficult to recover. The core quality was also quite good. We recognized deep on the left, deep marine turf cliniform slope, disoxic clay silt banding, deep marine. Humocky cross-stratified sand in the middle, at the top of cliniform in offshore shore phase transition. And on the right-hand side, storm-graded layers, which are typical of cliniform slope or even deeper in lower offshore. We met also in the middle light gray foreshore sediments with its high-energy cross-bedded sandstone And very important too, unconformities. And unconformities typical of a drop in sea level, we call sequence boundaries, with deep, and the second from the left, deep marine silty clay overlain by shallow marine coarse grained sand, or on the right-hand side, just deep marine disoxic clay, truncated by the unconformity again, and deeply burrowed and infilled by coarse grained glauconite sand from shallow marine sand. And on the left-hand side, so these two sequence boundaries are typical of a drop in sea level. And transgressive surface on the left-hand side, where you see a sharp boundary between sand, coquina sand or bioclastic sand overlain by dark gray offshore marine shell. This is a transgressive surface. The sea was rise. It's typical of a rise in the sea. And those surfaces are things we are collating regionally and sometimes worldwide to trace all around sea level change. Fauna in the sediment was a great help to define the depositional environment and paleobathymetry. This is a fantastic tool. As well, also, palynology is also a great tool to define how the past landscape and seascape look like. We have a full range of proxies there to define precisely the depositional environments. Our preliminary results are the following. We recovered continuous record of landscape and seascape evolution from 1,311 meters of shallow marine sediment. We identified ancient soil, beach, continental shelf sediment, indicating 10 cycles of 50 to 100 meters of sea level change from 14 to 35 million years ago. And we discovered lances of fresh water as much as 400 meters below the seafloor, 50 kilometers offshore. This was quite a surprise for us. And we detected climate change indicated by abrupt change in tree pollen carried offshore by ancient winds. This is the Expedition 313 Science Party in Bremen, where we opened the core. Thanks a lot for coming, listening to us.
Yeah, thank you, Jean-Noël and Dave. Just one short question, Jean-Noël. You said the freshwater lenses, which you found quite considerably well offshore, were kind of surprised. What do these freshwater lenses tell you then? How can you imagine Earth history? What has gone on? Any idea?
These freshwater lenses are quite deep below the seafloor. We found some freshwater lenses at 419 meters below the sea level. It's quite deep. And we think that this freshwater were probably fossilized on form during the last drop in sea level 18,000 years ago. And this period was a time where phreatic waters went offshore and then were buried during the last transgression. It's an hypothesis. We don't know yet, and Mike Motter from Hawaii University is working hard on that. There are a lot of things we are not understanding at that stage. Okay. It's something we are looking for, but...
Yeah. Thank you. So, any question from your side, which you would like to... Yeah, can you take the microphone, because it's this media conference, our web stream.
You said there were 10 cycles of 50 to 100 meter changes in sea level. Were those regular or irregular?
No, it's an average. They are irregular, yes. And they are irregular, and they occur at different time scales too. Some are of short time scale and some of longer time scale. We have the shortest we can see are about 500,000 years long, and the longer scale are a few million years long cycle of sea level change.
And can you calculate what was the reason for that? For the different periods, length of the period, and also for
yes, we are
lowering of sea level.
We have different different reasons for this variation, and this can be short-term tectonic change in the basement or worldwide change in the plate tectonics. And we have no clear reason at the moment, because we must backstrip our data. We must describe and calculate the load of a sediment on the crust, and how much the crust was deflected by the load of a sediment and of the water depth also. And it's a lot of work we have not done at the moment. It's a first appraisal. We know we have these cycles, and we have no clear idea on the causes at the moment. But we know we have different kind of sea level change, of cycle of sea level change, yes.
And if you link your data with the data of paleoclimatologists, is the picture getting clearer then? Yes,
we can correlate those change to the change recorded by our 18 variation. The timing is quite good, but the amplitude is not accurate for us at the moment. Yes, and we are working to precise the amplitude of sea level change. Yes.
But if you're going back, let's say 20 million years, like in your case, or 35 million years, which is quite a long time before man appears on the scene, yeah. Does it have any value for making present models for sea level rise more accurate? Or is it just pure knowledge you're gaining here?
It's basically pure knowledge, but the way sediment is we aim to understand better the way the sediment responds to sea level change, and if we understand that very well, we will help to understand better what is happening today for our shorelines. For example, we monitor multiple shifts of shoreline from onshore, offshore, and the shoreline crosses the shelf more than 10 times during this period, and we can follow it very precisely. And this is very important, because what we experience today is a shift of our shorelines everywhere. So if we understand better how the sediment respond to sea level change, it's quite good.
All right, any further questions? Herr Schrader?
How was life on board this platform? I mean, how many meters did you drill per day, and can you tell a little bit about what happened there in the daily routine?
Dave?
Yeah, I can answer this. On average, we were drilling about 30 meters per day. 30 meters per day. We had an average recovery of 80%, so we're looking at several tens of meters arriving on board every single day, which has to be curated on board. So it gets taken out of its plastic, it gets taken out of the core barrel, out of the drill pipe, and its plastic liner, plastic tube, and it gets cut into 1.5 meter sections, and it gets curated and stored in the refrigerated storage. But before it goes in there, we have a team of scientists who do some preliminary measurements on the core. So we have some geochemists who take some pore water samples. We have some petrophysicists who run the cores through what we call a multi-sensor track, which can measure 4 different physical properties on the core. So your question, what was life like on board? It was most times it was busy when the core was arriving on deck quickly. We had periods when there was perhaps when they were changing over some of the equipment, there was maybe a little bit of downtime, which allows the scientists to catch up in some of their work. Quite a small vessel, the Cade, as you saw in Jean-Noël's picture. It's quite a small platform, not a lot of room, and by the time we have all our containers and equipment loaded on, there's even less room. So you are kind of living on top of each other a bit. So it's important to maintain a high team morale, which I think we achieved. We had a good working environment. It's 3 months at sea. We had a rotated shift pattern, so some staff were coming on and off every so often, every 2 or 3 weeks. So nobody was stuck on there for 3 months in one go. It may have been a bit too much to ask to have somebody stay on there for 3 months. But it was a good ship, and the food was excellent, which helps a lot.
But there's some...
fresh seafood.
Yes.
We were lucky enough at that time.
Well, we could talk about the seafloor and the environmental aspects, but I would just like to point out there's one major difference between the US and the Japanese and the European expeditions. Whereas JOID's Resolution and GEOCU are real research vessels, as Dave pointed out, the platforms we are using, the European missions are using, they are chartered from time to time. So these are normal platforms used in oil business and other businesses. They are not research vessels. So on board, only basic measurements, urgent measurements, microbiology, for example, are being carried out, according, of course, to the high IODP standards. And that is what Jean-Noël pointed out, all other investigations are taking place during the so-called onshore science party. You know, we have this offshore phase and the onshore phase. And this picture you see there at the core repository in Bremen, there are 3 core repositories worldwide with the IODP program, one in Japan, one in Texas, and one in Europe. There, the real science, the hard science is going on, and it is, of course, being continued now. You are working on the course. Can you maybe, Jean-Noël, can you point out what is happening to the samples right now or in the next couple of months?
How many samples did we collect in Bremen? Do you remember? 15,000?
Yeah, 15 or 16,000 samples were taken from the cores.
So we are, and those samples are distributed among the different researchers of a group. We're 28 scientists, and we are working hard on them. And we will meet later in the year or early next year to just summarize and share our experience and show our results. But we need 1 year at least, at the very least. We have worked for 3 years probably.
As we have a colleague from Nature here, any idea when the first papers will be out?
For Nature?
Well, we can discuss with him, we can bargain with him.
Yes, we are publishing. I think we have planned 3 common papers by the end of the year. This year, 3 papers will come out, but there will be probably quite general papers on the main topics of the expedition, and then next year we will publish more specific papers on new things, really, and more precise things. Yes, more targeted.
I should maybe just add that in the beginning of December this year, we'll release our expedition report, which gets published online, and that will contain the results from the offshore part and also the onshore science party. But what Jean-Noël was talking about was the subsequent, what we call post-expedition research that the scientists do individually at their own labs and institutes.
Yeah, and you can, mentioning the web, there are 2 websites I would recommend. It's, the one is IODP.org. That's a general website, and you will find information in the media kit. IODP.org, it's the general website where you find all expeditions. And then the European missions, you can find them on www.ecord.org, ECORD.org. European Consortium for Ocean Research Drilling. And there the report you're talking about is also there, right?
We found there, yes.
Yes, preliminary and expedition report. Very soon.
All right. Yes. Any more questions? Yes.
What is special about New Jersey? What did you find there that you couldn't have found in the North Sea or something else closer to home that's equally shallow?
The very nice thing with the New Jersey thing is we have exposed there a wonderful set of clinoform, this prograding sandstone body progressively through time, and we can sample them because each of these clinoform was deposited during a cycle of sea level change. So we can measure the period of high sea level at the top of a clinoform and when the sea level was low in the middle or at the toe of a clinoform. So this helps us to measure the magnitude of sea level change at each clinoform progressional event.
May I ask you to translate the expression clinoform? Maybe is that very complicated? Is it possible?
Clinoform is the same word in French.
It's a challenge.
Prograding shore face or deltaic body. I try. These are clinoforms. These are clinoforms.
Yeah.
Oh, this. These are clinoforms. These are clinoforms. And you see here, for example, this clinoform is prograding. This is a shore face to deltaic sand body prograding seaward. And during a high period of high sea level, then sea level drop and you erode out the top of a clinoform and you put here some slope deposits, and all of this is symptomatic of slope rejuvenation during a drop of sea level. So this clinoform body is a full cycle of sea level change. Okay? And when sea level is high, you can measure when sea level is high because sediment is deposited here, but when sea level drop, you deposit sediment at the toe of clinoform. So you can capture a full cycle of sea level change at each of these clinoform body.
Yeah, Schmeier.
So, Corinne Giermeier from Nature, how did you know you would find these nice things off New Jersey? How was the drilling site identified in the first place?
Because for a long time now, from the 80s, we had several seismic surveys on the shelf, some for oil purpose, but some just for academic purpose. And we saw that on the seismic. This is a seismic image of the shallow marine platforms. And this clinoform, we have seen them because of the seismic surveys. And the good things also I forgot about in the New Jersey, on the New Jersey platform, it's a very tectonically stable platform and with a high sediment supply. So it's stable, we have not much trouble with tectonic, and we have high sediment supply. So the definition of the time is recorded with a lot of sediment. We have quite a thick package of sediment for every increment of time. It's better rather than having just a surface or just 2 millimeters of sediment. So high sediment supplies and high tectonic stability. It's very important too.
And the point was that this expedition was filling a gap, so to say, as Jean-Noël pointed out, between drilling efforts further offshore and drilling efforts on land.
Yes.
So, but this middle part, so to say, this middle section was missing. So this was filling the gap then.
And we didn't drill it before because we didn't have the right tools to do that. And the multiple platform tool is a fantastic tool to go in places which are difficult to drill. And we are very lucky for that. It's impossible for the gyres to drill there. And it's, yes, because it's too shallow and it's also very sandy. So it's quite difficult situation.
The water depth was 35 meters or something like
that,
right? Mm. So it's really...
So it's very important to have such flexible tool to go in very specific place to fill gaps in the data sets. And now we have in hand the full transect in the New Jersey through this platform. So we are very lucky.
Okay, any further questions? If this is not the case, in half an hour's time at 11 o'clock, we'll have the president of IODP here and the European director of this program, and they will tell about the future of ocean research drilling, because this program is running out in 2013, and we are currently discussing what comes next. And I think I would very much like to invite you to attend this media conference. So hopefully meet you in half an hour again. Thank you very much.
Thank
and
you.
Thank you.
Thank you very much.